Welcome back to the deep dive. Today, we're tackling something huge. We're asking a pretty profound question. When a star is born, is its final fate already sealed? Is its destiny as, say, a white dwarf or a black hole already written in the laws of
It
physics?
is. And that's not just a philosophical statement. It's one of the most incredible conclusions of 20th century physics.
Hmm?
And our guide for this journey is an absolute masterpiece of scientific thinking. The 1983 Nobel lecture by Subramanian Chandrasekhar.
Right, it's called On Stars, Their Evolution and Their Stability. And what I find so fascinating and why we wanted to do this deep dive is that you picture a star and you think of just chaos,
Right.
swirling plasma, magnetic fields, all these complex fusion reactions.
An absolute mess.
Yeah, a total mess. And yet, Chandrasekhar's argument is that all of that complexity, it kind of just washes away. The star's ultimate fate really comes down to a simple, unavoidable clash between the basic forces of the universe.
That's our mission today. We're going to follow his logic. We're going to see how gravity, which is the force that crushes everything, and quantum mechanics, which is the force that resists that crushing, and then relativity,
The ultimate speed limit.
the ultimate speed limit, how those three things combined to set these incredibly rigid, unavoidable limits on how massive a star can be and, whether it can even exist at all.
Okay, so to get started, let's use an analogy that Chandrasekhar himself uses to kind of set the stage. The atom.
Right. Atoms seem incredibly complex, but their basic properties, their size, and their stability are governed by just a few fundamental constants.
Like the Bohr radius, for instance. It's the simple formula that tells you the physical size of a hydrogen atom.
And it's just built from Planck's constant, the electron's mass, and its charge. That's it. It gives you the right answer for how big an atom should be.
And then there's the fine structure constant.
Yeah, which is another combination of constants. And it tells you something different. It tells you the maximum charge a nucleus can have before the whole atom becomes, unstable. Because the electrons are moving so fast, they become relativistic.
I see. So for an atom, you have one set of constants that defines its size and another that defines its ultimate stability. It's really neat.
It's very elegant. And so the challenge Chandrasekhar lays out is, can we do the same thing for a star? Can
Yeah.
we find a simple combination of constants that explains the most basic fact about them?
And that basic fact is their mass. We measure it in solar masses, which is, it's a ridiculous number. 2 times 10 to the 33 grams.
It's colossal.
Hmm.
But most stars that we see, the stable ones, are all clustered around that kind of magnitude. It's not like we see stars that are a billion times bigger or smaller. There's a natural scale for them.
And if the universe were different, if, say, gravity was a little bit stronger or hydrogen was a bit heavier, that scale would be completely different.
So we need to find that cosmic yardstick. And this is the key. This is the central piece of the whole puzzle. Chandrasekhar reveals the combination of constants that provides the correct measure of stellar masses.
And what are the ingredients? Because this is where you can start to see the forces battling each other just in the formula itself.
Okay, so the formula is basically mass is proportional to the speed of light cubed, divided by the gravitational constant to the power of 3/2 times the hydrogen mass squared. M is roughly c cubed over g to the 3/2 h squared.
Whoa, okay, let's unpack that, the denominator first. You've got G, the gravitational constant. That makes sense. Stars are all about gravity.
Right, g is the force trying to collapse it.
And you have H, the mass of a hydrogen atom, the basic building block.
The fuel, so the denominator is the crushing force of gravity acting on the fundamental unit of matter.
And in the numerator, you have C cubed, the speed of light cubed. Why is the speed of light the ultimate speed limit sitting there defining the mass of a star?
Because, as we're about to find out, the entire fate of a star hinges on whether the particles inside it, the ones fighting gravity, start getting close to that speed limit. Relativity is the ultimate arbiter of its destiny.
So this single formula, this ratio of the cosmic speed limit against the force of gravity and the mass of matter, that gives you the right size for a star.
It's the number that the entire physical theory of stellar structure has to, line up with. It's the sanity check for whether you can build a stable, shining object in our universe.
All right, so let's use that constant as our foundation and build up the physics of a stable star, like our sun. It's all based on something called hydrostatic equilibrium. What does that actually look like inside the star?
You could think of a star as being made of countless layers, like an onion. And for any given layer, gravity is pulling all the layers above it down, trying to crush it.
Right.
Hydrostatic equilibrium just means that the pressure pushing outwards from inside that layer has to be exactly strong enough to hold up the weight of everything on top of it.
So the whole game is about balancing that pressure against gravity.
Exactly. And the key is that the total pressure, let's call it P, isn't from just one source. It's the sum of two very different things. There's the gas pressure, P gas, and the radiation pressure, PRAD.
Gas pressure is the one we all get intuitively. You heat up a gas, the particles move faster, they push outwards. Simple.
It's the perfect gas law. It depends on temperature, density, the usual stuff.
Yeah.
But the radiation pressure, that's the really interesting one.
That's from the light itself.
It's from the photons.
Mm-hmm.
The core is creating so much energy that it's filled with light, with photons that are trapped, bouncing around. And every time a photon bounces off a particle, it gives it a little push, an outward push. And crucially, this pressure goes up as the fourth power of the temperature.
T to the 4. So if you double the temperature, the radiation pressure goes up 16 times. That's huge.
It's immense. And Sir Arthur Eddington was really the first person to realize just how important this radiation pressure is, especially in really massive stars. He basically said, in some stars, the structure is being held up more by light than by the gas itself.
He called it the happening of the stars. But how do we prove that this balancing act, this requirement for stability, mathematically forces that cosmic mass constant to appear?
This is where Chandrasekhar brings in a really elegant, kind of abstract piece of physics. It's a general theorem about the pressure at the very center of any stable star.
Okay, what does the theorem say?
It says that for a star to be stable, the actual pressure at its core, PC, has to be somewhere in between the pressures of two imaginary spheres.
Imaginary spheres.
Yeah, it's a thought experiment. Imagine one sphere that has the same mass as the star, but its density is uniform and equal to the star's average density. Then imagine a second sphere, same mass, but its density is uniform and equal to the star's much higher central density.
Okay, so one is sort of a fluffy, spread-out version of the star, and the other is a super condensed version.
Exactly. And the theorem states that the real pressure in the real star's core has to be somewhere between the pressures you'd calculate for those two idealized cases.
Why? What would happen if it wasn't?
Well, if the pressure was too low, lower than the fluffy sphere, it would mean the core wasn't condensed enough to support the outer layers. It would collapse. If it was too high, higher than the superdense sphere, it would imply the pressure gradient was wrong somewhere else. It would, blow itself apart.
So it's a mathematical cage. The pressure has to live inside the specific range for the star to be stable.
It's a very strict requirement. And now here comes the magic. You take the actual physical equation for pressure, the one that includes both gas and radiation, and you force it to obey this mathematical stability rule.
And when you do the algebra, what pops out?
After a whole lot of math, that exact combination of constants we started with, cubed over g to the 3/2 h squared, is what's left. The stability requirement forces the physics to reveal the fundamental mass scale of a star.
So it's not just some number we observe. The fact that stars have the mass they do is a direct consequence of the requirement that they have to be stable.
It is, and it gives you a practical result. It leads to a very complex equation, a quartic equation, that sets an absolute upper limit on how much radiation pressure a star of a certain mass can handle before it becomes unstable.
Let's make that concrete. What about for a star like our sun?
Okay, so when you plug the sun's mass into this stability equation, the math shows that the radiation pressure at its center cannot be more than 3% of the total pressure.
Only 3%.
Just 3. If our sun was somehow built differently, so that light was providing, say, 5 or 10% of the central pressure, it would be fundamentally unstable. It couldn't exist at its current mass. That 3% number is the direct result of applying these fundamental constants to the laws of stability.
Wow. Okay, so we figured out how a star stays alive, held in this perfect balance, but all stars burn fuel, and eventually that fuel runs out, which brings us to their fate and the discovery of, well, these incredibly weird objects called white dwarfs.
Right. White dwarfs are the leftover cores of stars like our sun. The star sheds its outer layers, and what's left is this stellar cinder. But it's a cinder with a density that's just mind-boggling. We're talking 10 to the 5 to 10 to the 7 grams per cubic centimeter. A teaspoon of it would weigh several tons.
They're just cooling down for eternity. But that density created a huge problem for the physicists of the day, right?
Yeah.
It led back to Eddington.
It did. Eddington saw this as a massive paradox. He came up with this brilliant line, a star will need energy to cool, which sounds Completely wrong.
How do you need energy to cool down?
Well, think about it. The star has compressed itself down to this insane density. It did that by radiating away a tremendous amount of energy over billions of years. The paradox is, if you could magically turn off gravity, the material shouldn't have enough energy left to expand back into normal atoms.
The particles are packed so tightly together.
So tightly that the electrostatic repulsion between the atomic nuclei is enormous. To push them apart back to the size of normal matter, you'd need a huge amount of kinetic energy, of heat. But the star has already radiated all its heat away. It's cooled down.
So it's trapped. It doesn't have enough thermal energy left to overcome the electrostatic forces holding it in this compressed state.
Exactly. It's locked in. It's a paradox.
Mhm.
How can something that got this dense by cooling down be unable to decompress because it's too cool?
And the solution to this, it didn't come from classical physics. It came from the brand new and very strange world of quantum mechanics.
Specifically from a landmark 1926 paper by R.H. Fowler called Dense Matter. Fowler was the first to apply the rules of quantum mechanics, specifically Fermi statistics and the Pauli exclusion principle, to the inside of a star.
This is the idea of electron degeneracy, right?
That's the one. Let's try to explain it. In a normal hot gas, electrons can have any energy they want. But the Pauli exclusion principle says that no two electrons can be in the exact same quantum state. They can't occupy the same seat, so to speak.
Okay.
When you crush matter to white dwarf densities, you force all the electrons into a very small space. They're forced to fill up all the available low-energy states.
It's like filling seats in a stadium, starting with the cheap ones at the bottom.
Perfect analogy. Once all the low-energy seats are full, if you want to cram more electrons in, you have to put them in the higher-energy seats. You're forcing them into states of very high momentum, making them move incredibly fast, even if the star is technically very cold.
Ah, so their motion isn't from heat. It's because they're being forced into high-energy states by quantum rules, and that motion creates pressure.
An enormous pressure. And here's the crucial insight from Fowler. This is degeneracy pressure, and it's completely independent of temperature. The kinetic energy that comes from this is called zero-point energy.
So the star doesn't need to be hot to hold itself up anymore. It's using this built-in quantum energy.
And Fowler realized this zero-point energy can't be radiated away. It's locked into the quantum structure of the matter. It solved Eddington's paradox. The white dwarf is stable because it's essentially acting like one single gigantic molecule in its lowest possible energy state.
That's a powerful image, a star-sized molecule. So once you have this new source of pressure, what does the model predict for the star's structure?
Well, in this state, the physics gives you a very clean relationship between pressure and density. And that relationship allows you to model the star as something called an Emden polytrope of index n equals 3/2.
A polytrope is just a mathematical model for a ball of self-gravitating gas, right?
Right. And this specific n equals 3/2 model was beautiful. It predicted that you could have stable white dwarfs at any mass. But more importantly, it predicted a very specific and very strange relationship between mass and radius.
Okay, what was it?
It predicted that the radius of the star is inversely proportional to the cube root of its mass.
Wait, hold on. Let me make sure I'm hearing that right. You're saying that if you add mass to white dwarf, it gets smaller.
That's what the math says. And it's completely counterintuitive.
Yeah, it is. Why does that happen?
Because of what's holding it up. If you add more mass, gravity gets stronger. To fight that stronger gravity, the degeneracy pressure has to increase. And the only way to increase degeneracy pressure is to squeeze the electrons even closer together to increase the density.
And higher density means a smaller radius. Wow, so the star literally shrinks to fight back against gravity.
It does. And this model was a huge success. For a white dwarf with the mass of our sun, it predicted a radius and a density that perfectly matched what astronomers were actually observing.
So for a while, everyone thought, problem solved. Quantum mechanics explains it all. Any star, no matter how big, will eventually end up as a stable white dwarf.
That was the thinking. But that simple, elegant model had a hidden flaw, a relativistic flaw.
Right. This is where it all breaks down and where we get to the Chandrasekhar limit itself. Why did this beautiful quantum theory fail?
It failed because of that inverse relationship we just talked about. As you add more and more mass, the star gets smaller and smaller, and the density gets higher and higher.
And as the density goes up, the electrons are forced into those higher and higher energy states.
Meaning they're forced to move faster and faster. Eventually, their speeds start to approach the ultimate speed limit in the universe, the speed of light, c.
And this wasn't just some abstract high mass problem.
Not at all. Chandrasekhar calculated that even in a regular one solar mass white dwarf, the electrons at the center are already moving at about 63% of the speed of light.
Once you're dealing with speeds like that, you can't use the simple Newtonian formulas for energy and momentum anymore. You have to switch to Einstein's special relativity.
And that one mathematical change, switching to the relativistic formula for kinetic energy, completely alters the physics of the star. It changes the fundamental relationship between pressure and density.
In the stable non-relativistic case, the pressure was proportional to density to the power of 5/3. What does it become when the electrons are relativistic?
As the electrons get faster and faster, in the highly relativistic limit, the relationship changes. The pressure becomes proportional to density to the power of 4/3.
That seems like such a small change, from 5/3 to 4/3. Why is that so catastrophic?
Because it fundamentally changes the stiffness of the gas. The gas doesn't push back as hard when you compress it, and it shifts the theoretical structure of the star from that stable n equals 3/2 polytrope to a critically unstable one, the n equals 3 polytrope.
And what's special about the n equals 3 polytrope?
It has a unique and devastating property. For a star modeled with this structure, its total mass is uniquely determined by the physics. It doesn't depend on the radius anymore.
Wait, the mass is fixed, independent of the radius. What does that even mean for a star?
It means there is an absolute upper limit to the mass of a star that can be supported by electron degeneracy pressure, a limiting mass. As you approach that limit, the pressure just can't keep up with gravity anymore. Mathematically, the radius shrinks to zero. The star is on the brink of total gravitational collapse.
And that is the Chandrasekhar limit.
That is the limit. And here's the most beautiful part. When you do the calculation to figure out what that limiting mass is, what combination of constants defines it?
Let me guess. It's c cubed over g to the 3/2 h squared.
It's the exact same combination of fundamental constants that define the mass scale of a normal living star. The constant that sets the scale for life also sets the absolute limit for death.
That's incredible. It's a cosmic bookend. And that limit is about 1.4 times the mass of our sun. Any star whose leftover core is heavier than that simply cannot become a white dwarf. It has to keep collapsing. Its fate must be something else entirely.
Its fate is something far more violent.
Okay, so 1.4 solar masses is the line in the sand. Now we have to figure out how a living star actually gets to a point where it's either above or below that line. This brings us to the actual evolution of stars.
Right. We know degeneracy pressure is the star's salvation, but it doesn't always kick in. The key is that degeneracy can only happen if the radiation pressure, the light pressure we talked about earlier, isn't too strong.
If the radiation pressure is too dominant, it keeps the core hot and fluffy, I guess. It prevents it from condensing enough for the quantum effects to take over.
Exactly. The core needs to get incredibly dense for degeneracy to happen. And the physics sets a very specific boundary. For degeneracy to become the dominant support mechanism, the radiation pressure has to be less than about 9.2% of the total pressure.
9.2%. That's a very specific tripwire. So how does that relate to the total mass of the star?
Well, we go back to Eddington's standard model. It showed that as a star gets more massive, it gets much, much hotter in the core. And because radiation pressure goes as temperature to the fourth power, that pressure becomes dominant very quickly in massive stars.
The bigger the star, the more it's held up by its own light.
Precisely. And Chandrasekhar used those models to show that in any star more massive than about 8 solar masses, the central radiation pressure is always greater than that 9.2% limit.
So that's the dividing line. Stars above 8 solar masses are too dominated by radiation pressure. They can't form a stable, degenerate core early in their lives.
Their path has to be radically different. Unless they somehow manage to blow away most of their mass, their fate is sealed. For them, only the most violent possibilities are left.
Let's follow that path then. For a star more massive than 8 suns, what happens when it runs out of its primary fuel?
Without degeneracy to halt the collapse, the core just gets hotter and denser. Unimaginably so. This allows it to ignite heavier and heavier elements. It burns through its hydrogen, then its helium, then it starts fusing carbon, then neon, oxygen, all the way down the periodic table.
Until it gets to iron, because you can't get energy by fusing iron.
Right, iron is the ultimate ash. But something else happens in those extreme conditions. The fusion of these heavier elements produces a flood of neutrinos.
And neutrinos barely interact with anything. They just fly right out of the star.
Instantly. And they carry away enormous amounts of energy. This neutrino emission is like a refrigerator for the core. It cools it down incredibly efficiently. which reduces the radiation pressure, which causes the core to contract even more.
It's a runaway process. More contraction leads to hotter fusion, which makes more neutrinos, which cools the core, which leads to more contraction.
It's a death spiral. And it continues until the core becomes so dense that it is finally, catastrophically, forced into a state of relativistic degeneracy. And the mass of that core, it's going to be right around 1.4 solar masses.
Right at the Chandrasekhar limit. And as soon as it hits that limit, it's unstable.
The collapse is instantaneous. It happens in less than a second. The core implodes until it's stopped by an even stronger form of quantum pressure, neutron degeneracy. The outer layers of the star, which were falling in, slam into this newly formed, incredibly hard neutron core and rebound outwards in a spectacular explosion.
Type 2 supernova.
A Type 2 supernova. And what's left behind is either a neutron star or, if it's too massive, a black hole. And the evidence is just beautiful. When we measure the masses of pulsars, which are neutron stars, they consistently cluster right around 1.4 solar masses. The theory perfectly predicted the mass of these cosmic remnants.
Okay, what about the stars in the middle, say between 6 and 8 solar masses? They're below that threshold where radiation pressure dominates.
Right, so they can form a degenerate core early on, a stable, non-relativistic one. But they're still massive enough to keep burning fuel in a shell around that core.
So the core sits there, and the ash from the burning shell just keeps falling onto it, making it heavier.
It just grows and grows, slowly, over millions of years, until
it hits 1.4 solar masses.
And the same relativistic instability kicks in. It triggers an explosion, which we believe is the cause of a different kind of supernova, a Type I supernova. So the same physical limit is responsible for both major types of stellar explosions.
That's amazing. And what about the really small stars, the red dwarfs?
The theory shows that for stars less than about 0.43 solar masses, they can never get hot or dense enough in their cores to trigger any of this. The maximum pressure they can generate is always less than what degeneracy pressure can provide.
So there are no surprises for them.
No surprises. Their fate is sealed from the start. They will simply burn through their fuel over trillions of years and fade away into a quiet, stable white dwarf. Their destiny is fixed.
So we've seen how special relativity sets this absolute mass limit. But that's not the end of the story. Now we have to bring in the full force of Einstein's theory of gravity, general relativity, which introduces a whole new set of dangers.
These are instabilities that have no equivalent in old Newtonian physics. They arise purely from the fact that massive objects warp the fabric of space-time itself. The first one is called radial instability.
Okay, so in the old physics, the stability of a star against, say, pulsing in and out was all about how stiff the material inside it was, this property called the adiabatic exponent.
Right. If that exponent, gamma 1, dropped below 4/3, the material was too squishy and couldn't resist collapse.
So stiffness was all that mattered.
In Newtonian physics, yes. But in general relativity, stability also depends on the star's physical size, its radius, compared to its Schwarzschild radius.
The Schwarzschild radius, just to remind everyone, is the point of no return. It's the radius of the event horizon for a non-spinning black hole.
It's defined as 2gm over c squared. And it's the scale at which gravity becomes overwhelmingly dominant.
So you're saying that even if the star's core is made of the stiffest material imaginable, it can still become unstable just by being too small, too compressed?
Exactly. General relativity sets an absolute limit on compactness. The theory shows that no stable object can exist if its radius shrinks below 9/8 of its Schwarzschild radius.
9/8. That's 1.125. So if you get within 12.5% of your own event horizon, you are doomed to collapse no matter what you're made of.
It's the ultimate cutoff. The geometry of spacetime itself ensures your collapse.
But the really dramatic part is something called the post-Newtonian effect, which kicks in much, much earlier.
Yes, this is what's relevant for those massive stars we were talking about. In a very massive, centrally condensed star, where radiation pressure is important, that stiffness index is only slightly above the 4/3 danger zone. In that case, the general relativistic instability can set in when the star's radius is still enormous compared to its Schwarzschild radius.
So the star is doomed long before it gets anywhere near that 9/8 limit.
Absolutely. The calculations show that for these massive stars, this global instability can be triggered when the radius is still 5,000 times the Schwarzschild radius. The whole scar becomes unstable at once, triggering that final catastrophic collapse.
And this instability, it actually gave us a test for what pulsars are.
It did. The same theory predicts that a white dwarf, a degenerate configuration, has a minimum possible pulsation period. It can't oscillate faster than about once every 2 seconds.
If it did, it would have to be too small and too dense, and this relativistic instability would destroy it.
Correct. So when pulsars were first discovered, spinning hundreds of times a second,
They couldn't be white dwarfs.
they couldn't be white dwarfs. They had to be something much, much smaller and denser. They had to be neutron stars. The instability theory provided the proof.
That's brilliant. Okay, what's the second type of relativistic instability? The one that deals with rotation and gravitational waves.
This one is called secular instability. We have to think about rotating stars. Classically, a rotating ball of fluid takes on a squash shape, a Maclaurin spheroid. As it spins faster, it gets more squashed.
Until it just flies apart.
Well, before that, Lord Kelvin figured out that if the fluid has any viscosity, any internal friction, it becomes unstable at a certain point and will spontaneously change its shape into a 3-axis ellipsoid, like a potato, a Jacobi ellipsoid.
Because that's a lower energy state for the same amount of spin.
Exactly. Now, general relativity introduces a new, much more powerful form of friction, the emission of gravitational waves. Any spinning object that isn't perfectly symmetric is constantly radiating away energy and angular momentum as ripples in spacetime.
So you'd think the gravitational waves would just take the place of viscosity and drive that instability, right?
That's what everyone thought, but surprisingly, no. It turns out that because gravitational radiation carries away both energy and angular momentum, it actually stabilizes that particular mode.
So what does it destabilize?
It destabilizes a different, more subtle mode of oscillation related to the internal fluid motions of the star. It's called the Dedekind mode. This instability, driven by gravitational wave emission, is what we now believe limits how fast a brand new pulsar can spin.
I see. So a newborn neutron star is spinning insanely fast. It immediately starts shedding angular momentum through gravitational waves, which triggers this internal instability, which acts as a brake, slowing it down to a more stable rotation rate.
It's a perfect example of how the grand laws of general relativity reach down and control the millisecond spin of a tiny collapsed stellar core.
So this whole path from stability to quantum mechanics to the relativistic mass limit and finally to these fatal GR instabilities, it all points to one inevitable conclusion.
The formation of black holes. In Chandrasekhar's view, their existence as the endpoint for massive stars is, and I quote, inescapable. Once you're past the mass limit and you collapse below that 9/8 radius, there are no forces left in the known universe that can stop you.
And we know what they are. A region of space-time bounded by an event horizon. But it's the mathematics of black holes, the Kerr solution, that Chandrasekhar found to be the most profound part of the whole story.
Yes. When you apply the laws of general relativity and you assume the black hole is stationary and isolated, the theory gives you exactly one and only one family of solutions, the Kerr family of rotating black holes.
And it's defined by just two parameters. I mean, the star that made it was this incredibly complex beast with magnetic fields and fusion shells and all this history, and it all boils down to two numbers.
That is the big revelation. It's the no-hair theorem. Every single isolated, stable black hole in the universe is described completely and perfectly by just its mass and its angular momentum, its spin. That's it.
All that other information, its composition, its temperature, its history is just gone, wiped clean when it crosses the event horizon.
Chandrasekhar found this simplicity just staggering. He contrasted it with any object here on Earth. A table, a rock, anything. They are governed by this messy combination of forces and require endless approximations to describe.
Right. A table is quantum mechanics and chemistry and thermodynamics all jumbled together.
But a black hole is made of pure space and time. It is, in his words, the most perfect macroscopic object there is in the universe. It's the simplest because we have an exact, perfect mathematical formula for it.
And that mathematical perfection is deep. It's not just a simple description.
Not at all. It turns out that all the standard equations of physics can be solved exactly inside the warped space-time of a Kerr black hole. The math is as clean and perfect as the object itself.
This is why he ended his Nobel lecture with these old philosophical mottos, right, about simplicity and truth.
Yes, he saw the entire journey through all the complex physics of a star's life and death, as culminating in an object of singular mathematical beauty. The simple is the seal of the true.
What an incredible intellectual arc we've just followed. We've traced the entire destiny of stars just by following the logic in Chandrasekhar's lecture.
We started with that basic requirement for a star to even exist, to be stable, and out of that popped this fundamental constant that sets the mass scale for all stars.
Then we saw quantum mechanics come to the rescue with degeneracy pressure, creating the white dwarf, only to see special relativity impose a hard limit on that salvation, the Chandrasekhar limit.
And that limit, in turn, explained why massive stars have to follow this violent path of supernova explosions, creating neutron stars and black holes.
And finally, general relativity came in with the final knockout blows, the instabilities that guarantee that collapse, once started, is total and irreversible, leading to the mathematically perfect black hole.
I think the biggest takeaway for you, listening to this, is that a star's ultimate fate isn't a matter of chance. It's not determined by the chaotic details of its life. It is fixed from the very beginning by a handful of numbers, the fundamental constants woven together by the rigid rules of physics.
And that leaves us with a final provocative thought. If the unimaginable complexity of a collapsing 50 solar mass star can resolve itself into an object as profoundly simple as a black hole, described by just two numbers, what other messy, complex systems in the universe, maybe even here in our own world, are just hiding a simple, elegant, underlying truth?
Where else does chaos and complexity ultimately yield to a devastatingly simple and beautiful answer? That, I think, is the question he leaves us with.
A perfect place to end. Thank you for taking this deep dive with us. We'll see you next time.